In this lecture, we're going to be talking about divisibility, and we're going to be distinguishing between dividing and dividable. Now, it is easy to add and multiply natural numbers in general. If we extend our focus to all integers, then subtraction is also easy. We need the negative numbers so we can subtract any number from any other number, even larger from smaller numbers. Division is the first operation that presents a challenge. If we wanted to extend our set of numbers so any division would be possible, maybe excluding division by 0, we would need to look at the rational numbers like 2/3, 1/2, 5/6, or 6/5, the set of all numbers which can be written as fractions. This would be going too far, so we will refuse this option. In fact, it is a good thing that not every number can be divided by other numbers. This helps us understand the structure of the natural numbers and opens the door to many interesting questions and applications. If given numbers a and b, is it possible that a divided by b, oh, that's an eraser, there we go. Is it possible that a divided by b gives a whole number? In this case, we say that b divides a in symbols and we write b divides a. That should be completely vertical technically. If this holds, then b is a divisor or factor of a, and a is a multiple of b. In other words, if b divides a, then a equals b times k for some k that's an integer, natural number, however you want to describe it. This is saying a is some multiple of b. Now, I work with the integers, even though some courses work with just natural numbers. They're almost equivalent, and the difference is honestly not that significant whatsoever. All right, let's take a look at all of this wrapped neatly together. This is called the divisibility relation. Given integers m and n, we say m divides n, and we write m vertical bar n, provided n divided by m is an integer. Thus, the following assertions mean the same thing. So all four of these are all exactly equivalent. They're logically equivalent. Everything that they're saying is essentially the same. M divides n. N equals m times k for some integer k. M is a factor or divisor of n, and n is a multiple of m. Notice that m divides n is a statement. This right here, and this is going to be weird, that right there is a statement. It is either true or false. That's not the result of dividing n by m. That's not a number. What you're looking at is not a number there. That right there is either true or false. That's the result. The result of that is either true or false. So if I write 5 divides 10, that is the same thing as saying true. But if I write 5 divides 11, that's the same thing as saying false. These are statements. They're statements. They're not operations. They're statements. There's a huge difference between the two there. If I said 10 divided by 5, that's not a true or false statement. That's just 2. But this right here is not 2. Do not replace 5 divides 10 with 2. Because 2 is not true or false, 2 is just an object. We don't identify whether that object is true or false because it's not something that's true or false. It's not a statement, it's a number. So, on the other hand, n divided by m or n over m is some number. So if we want to claim that m divided by m is not an integer, so m does not divide n, then we can write m does not divide n. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below, and make sure to click on that subscribe button. All right, let's do an example together to wrap this all up. Decide whether each of the statements below are true or false. 4 divides 20, 20 divides 4, 0 divides 5, and so on. Let's start with number 1. This is true. 4 goes into 20 5 times without remainder. In other words, 20 divided by 4 is 5, which is an integer. We could also justify this by saying that 20 is a multiple of 4 because 20 is 4 times 5. Now let's look at number 2. This is false. While 20 is a multiple of 4, it is false that 4 is a multiple of 20. Number 3. This is also false because 5 divided by 0 is not even defined, let alone an integer. Number 4 is actually true. In fact, in general, and I'll write this out, any integer x divides 0. Why? This is because 0 is a multiple of every number, every integer, because 0 equals x times 0. So 0 is a multiple of x because we can replace that k integer with 0. In fact, let's do number 5, which is also an interesting result, very similar. 7 divides 7 is true because, in general, x divides x for all integers x every single time because x is 1 times x. It's a multiple of x. All right, let's look at 6. 6 is true because 1 divides every number. In fact, you can always write 1 divides x for all x because x equals x times 1. X is a multiple of 1. You just multiply that 1 by whatever your integer x is. Let's look at 7. 7, a little tricky because we threw in that negative number there, but this is still true. Negative numbers work just fine for the divisibility relation. Here we can say 12 is negative 3 times 4. Not 4, negative 4. So 12 is a multiple of negative 3. Looks a little weird, but that's how we would write it. Now, let's look at 8. 8 is false. Both 8 and 12 are divisible by 4, but this does not mean that 12 is divisible by 8. And then lastly, 9. 9's a little bit complicated here. Let's take a look at 9 because this is going to lead into the next lecture as well. So pay very careful attention to this one. 9 is false. This last example raises a question though. How might one decide whether any number divides any number in general? Of course, if you had a trusted calculator, you could ask it for the value of 136,299 divided by 1,642. If it spits out anything other than an integer, you know that the first does not divide the second here, or m does not divide n. This seems a little like cheating though. We don't have division in general, so should we really use division to check divisibility? Seems slightly circular. While we don't really know how to divide, and at least at this point, we do know how to multiply. We might try multiplying by larger and larger numbers until we get close to 136,299. How close? Well, we want to be sure that if we multiply 1,642 by the next larger integer, we go over that number. For example, let's try to decide whether 1,642 divides 136,299. Start finding multiples of 1,642. Here we go. 1,642. Let's try times 2, which is 3,284. Okay, let's do, that didn't work, so let's try 3. 1,642 times 3, which is 4,926. Okay, that didn't work. I'm trying to get 136,299, or just a little bit over, just a little bit under. Let's try for it. 1,642. And you probably figure where I'm going at with this. This is a really inefficient method. This, by the way, is 6,568. All of these are well less than 136,299. I suppose we can jump ahead a bit. Maybe we can try 1,642 times, instead of 5, let's do 50. This is 82,100, excuse me. Let's try 1,642 times 80. This is 131,360. Okay, we're getting kind of close here, but we're still a little bit off. We're off by about 5,000 now. So we're getting close. Let's slow down a little bit with this quotient here. Let's try 85. 1,000, and I'm going to give myself a little bit of room here. 1,642 times 85 equals 139,570. So we need to look somewhere between 80 and 85 because 80 was a little bit too little and 85 was a little bit too much. Let's try 83. So 1,642 times 83. Well, this is 136,286. Ooh, that is really close. Very, very close. Is this the best we can do? How far are we from our desired 136,299? If we subtract, we get, if we subtract the two here, let's do 136,299 minus that value. Let's see what our remainder is. We get 13, it looks like. So we know we cannot go up to 84. That will be too much. In other words, we found that 136,000, let me give myself a little bit room so that you all can see properly. All right, so we found that 136,299 is 83 times 1,642 plus a remainder of 13. Now, since 13 is strictly less than 1,642, we can now safely say that 1,642 does not divide 136,299. Anyways, thanks everyone, and I'll see you in the next video.